Welcome! Today, we'll explore LeetCode problem number 1798, titled Maximum Number of Consecutive Values You Can Make. This problem challenges us to think creatively about constructing consecutive integers using an array of numbers. Let's dive in and break it down step by step. In this problem, we are tasked with finding the maximum number of consecutive integer values that can be formed starting from 1 using the coins provided in the input array. Each coin in the array has a specific value, and you are allowed to use any number of each coin to form sums of money. The goal is to calculate the longest sequence of consecutive sums, beginning from 1, that can be constructed using these coins. The input consists of an array coins containing integers representing the value of each coin, and the output is a single integer, which is the maximum number of consecutive values starting from 1 that can be formed. Let's explore some examples to understand this problem better. Consider the first example where the input is coins equals 1, 3. Here, you can form the value 1 using the 1 valued coin. However, you cannot form the value 2, as there is no combination of the given coins that produces this sum. You can form the value 3 using the 3 valued coin, but since 2 is missing, the sequence of consecutive values starting from 1 ends at 1. Therefore, the output in this case is 2. As the maximum number of consecutive values starting from 1 is just 1 and 2. In this scenario, the gap at 2 prevents a longer sequence. Now, let's look at another example with coins equals 1, 1, 1, 4. Here, you can form 1, 2, and 3 by using different combinations of the 3 1-valued coins. Adding the 4-valued coin allows you to extend this sequence to include 5, 6, 7, and 8, resulting in a total of 8 consecutive values starting from 1. Since there are no gaps in the sums from 1 to 8, the output for this example is 8. This demonstrates how larger coins can help extend the sequence when smaller coins already cover the initial values. For the next example, consider coins equals 5, 7, 1, 1, 2, 3, 22. Using the smaller coins, you can form sums from 1 all the way to 20 without any gaps. This is achieved by combining the values of the 1, 2, 3, 5, and 7 valued coins in various ways. However, after 20, it becomes impossible to form certain values consecutively, as there are gaps in the possible sums. Therefore, the output in this case is 20, since the maximum number of consecutive values starting from 1 is 20. Finally, let's consider some edge cases. If there is only one coin, such as coins equals 1, then the output is 1, as only the value 1 can be formed. If all the coin values are large, like coins equals 10, 20, 30, you cannot form smaller values such as 1, meaning the output is 0. Additionally, when there are duplicate coins in the array, such as coins equals 1, 1, 1, these duplicates do not change the result since the coins are treated as unique values for computation. These scenarios highlight the importance of understanding the distribution and value of the coins when solving this problem. To solve the problem of finding the maximum number of consecutive integers starting from 1 that can be formed using the given array of coins, several approaches can be considered. The brute force approach involves generating all possible sums of subsets of the array. This can be achieved using recursion or bit manipulation, and the results are stored in a set to keep track of unique sums. Once all sums are calculated, we can iterate from 1 upwards to determine how many consecutive values can be formed. However, this approach is computationally expensive, with a time complexity of 2 to the power of n, where n is the size of the array. As the number of subsets grows exponentially, this method becomes impractical for larger inputs. Another approach, the optimized greedy strategy, takes a different route. By sorting the coins and maintaining a range of consecutive integers that can be formed, we iteratively extend the range whenever a coin can fill the gap. If a coin cannot extend the range, the process ends. This method is significantly more efficient and avoids the overhead of generating subsets. The optimized greedy approach works as follows. After sorting the array, we begin with an empty range, represented as 1, 1. For each coin in the sorted array, we check if it can be used to extend the range. This is possible if the coin value is less than or equal to the upper limit of the current range. If so, the range is updated to include the new coin, effectively extending the sequence of consecutive integers. If a coin exceeds the range's upper limit, it means we can no longer form all integers consecutively starting from 1, and the process stops. The time complexity of this approach is O(n) log n, due to the sorting step, followed by a single pass through the array, which takes O(n). The simplicity of this method comes from the observation that, once sorted, the problem reduces to a straightforward check of whether each coin can bridge the next gap in the sequence. While other approaches like dynamic programming can also solve the problem, they are less efficient due to their higher time and space requirements. Among the approaches considered, the greedy strategy emerges as the optimal solution. The main insight is that sorting the coins allows us to process them in increasing order, simplifying the task of maintaining a range of consecutive integers. This approach is both time efficient, with a complexity of O(n) log n, and space efficient, requiring only O(1) additional space. When comparing the greedy method to alternatives like brute force or dynamic programming, the advantages become clear. The brute force method, with its exponential complexity, is infeasible for large inputs. While dynamic programming guarantees correctness, its higher time and space requirements make it less suitable for this problem. The greedy approach, on the other hand, is simple, elegant, and leverages the sorted order of coins to achieve the desired result efficiently. That said, there are trade-offs to consider. For smaller inputs or cases where enumerating all possible sums is necessary, dynamic programming or even brute force might be better suited. However, for larger inputs, the greedy strategy strikes the right balance between efficiency and simplicity, making it the most practical choice. In conclusion, the greedy approach provides the best solution for this problem, balancing efficiency and clarity. By iteratively extending the range of consecutive integers that can be formed, it ensures correctness while minimizing computational overhead. Sorting the coins at the start enables a structured and logical progression, and the method avoids the exponential or quadratic complexities associated with the alternative approaches. This makes the greedy strategy not only effective but also intuitive and easy to implement. By processing coins in increasing order and focusing solely on maintaining the range of achievable integers, we achieve a solution that is both practical and scalable for large inputs. To solve this problem, we need to determine the maximum number of consecutive integers starting from 1 that can be formed using the denominations provided in the coins array. The key idea here is to construct these sums incrementally, ensuring there are no gaps in the sequence. A greedy approach is ideal for this, as it allows us to process smaller coin denominations first. By doing so, we can build up the range of sums step by step, ensuring continuity. However, if we encounter a coin that is larger than the next consecutive value we need to form, the sequence breaks, and we cannot extend the range further. Sorting the coins in ascending order is a critical step in implementing this strategy efficiently, as it guarantees that we process smaller values first, aligning with the greedy approach. To implement the algorithm, we start by sorting the coins array in ascending order. This ensures that we process the smallest denominations first, which is essential for forming smaller sums that act as building blocks for larger ones. Next, we initialize a variable max_consecutive to 0, which will keep track of the maximum range of consecutive sums we can form starting from 1. Initially, since no coins have been processed, this value is 0. As we iterate through the sorted coins array, we check each coin to see if it can extend our sequence. If the coin's value is greater than max_consecutive plus 1, it creates a gap, and the sequence cannot be extended further, so we stop. Otherwise, we add the coin's value to max_consecutive, effectively extending the range of consecutive sums we can form. This incremental approach ensures that every step contributes directly to maximizing the range. Once all coins have been processed, the value of max_consecutive represents the maximum range of consecutive integers we can form starting from 1. This is the result that we return. The algorithm relies on simple data structures, the input coins array, which is sorted for efficient processing, and the max_consecutive variable, which tracks the current range of sums. The time complexity is dominated by the sorting step, which takes O(n) log n, while iterating through the array takes O(n), resulting in an overall complexity of O(n) log n. Space complexity is minimal, as we only use O(1) additional space for the max_consecutive variable and do not create any auxiliary data structures. Let's go through an example to see the algorithm in action. Consider the input coins equals 1, 2, 5. First, we sort the array, which gives 1, 2, 5. We then initialize max_consecutive to 0. Processing the first coin, 1, we add it to max_consecutive, updating its value to 1. This means we can now form the sum 1. Next, we process the coin 2. Adding it to max_consecutive gives 3, so we can now form the sums 1, 2, and 3. Finally, we process the coin 5, but since 5 is greater than max_consecutive plus 1, which is 4, we stop. The result is max_consecutive equals 3, meaning we can form the consecutive integers 1, 2, 3. Now let's discuss some edge cases. If the array is empty, no coins are available, so the output is 0, as no sums can be formed. For a single coin, such as coins equals 7, we can only form the sum 1 if the coin's value is greater than 1, resulting in an output of 1. For arrays with large gaps, like coins equals 1, 10, we can form the sum 1 with the first coin, but the gap caused by the second coin prevents further sums, so the output is also 1. Key optimizations in this approach include sorting the coins to process smaller denominations first and breaking early when a gap is encountered, avoiding unnecessary computations. These techniques ensure the algorithm is both efficient and robust. The given code solves LeetCode problem number 1798, maximum number of consecutive values you can make, using a greedy algorithm. Here's a detailed breakdown of the solution. 1. Sorting the coins. The first step sorts the input list of coin denominations in ascending order. This ensures that smaller denomination coins are processed first, which is crucial for forming the maximum range of consecutive sums. 2. Initializing the range. The variable max_consecutive is initialized to 0. This variable represents the largest consecutive integer that can currently be formed from the coins processed so far. 3. Iterating through coins. The algorithm iterates through each coin in the sorted list. If the current coin is greater than max_consecutive plus 1, there is a gap in the range of consecutive sums that can be formed. This means it is impossible to form some values, so the loop terminates. Otherwise, the coin is added to max_consecutive, extending the range of consecutive sums that can be formed. 4. Returning the result. After processing all coins, the function returns max_consecutive plus 1, which is the total count of consecutive integers that can be formed starting from 1. Example walkthrough. Suppose the input is coins equals 1, 3, 1, 1. 1. Sort the coins 1, 1, 1, 3. 2. Initialize max_consecutive equals 0. 3. Process the first coin, 1. Extend max_consecutive to 1. 4. Process the second coin, 1. Extend max_consecutive to 2. 5. Process the third coin, 1. Extend max_consecutive to 3. 6. Process the fourth coin, 3. Extend max_consecutive to 6. 7. Return max_consecutive plus 1 equals 7. This greedy approach ensures optimal performance with a time complexity of O, n log n, due to sorting and a space complexity of O, 1. Here, we begin by importing the necessary utilities and defining our solution class. The main method of interest is getMaximumConsecutive, which takes an array of integers representing coin denominations. First, we sort the coins in ascending order to ensure we process them in a logical sequence. Then, we initialize a variable maxConsecutive to 0, which will keep track of the maximum range of consecutive integers we can form. Now, we iterate through each coin in the array. The key idea here is to check if the current coin is greater than maxConsecutive plus 1. If it is, this means there's a gap, and we can't form all consecutive values up to that point, so we exit the loop. Otherwise, we extend the maximum consecutive sum by adding the value of the current coin. This allows us to progressively build up the range of consecutive sums we can achieve with the given coins. Finally, the method returns maxConsecutive plus 1 to include the next consecutive value after the range we've calculated. In the main method, we demonstrate how to use the getMaximumConsecutive function. We define an example array of coins, 1, 3, 1, 2, which contains some duplicate and unsorted values. We then call the method with this array and print the result, which in this case is 8. This output means that with these coins, we can form all consecutive values from 1 to 8 without any gaps. The example helps illustrate how the algorithm works in practice, processing the coins to determine the maximum consecutive range of values that can be formed. This concludes the implementation, showcasing the simplicity and efficiency of the solution. To solve this problem, we begin with the first example where the input coins are 1, 3. The first step is to sort the coins, though in this case, they are already sorted as 1, 3. We then initialize a variable max_consecutive to 0, which will keep track of the maximum consecutive values we can form. Starting with the first coin, which is 1, we check if it is greater than max_consecutive plus 1. Since 1 is less than or equal to 1, we can include this coin and add its value to max_consecutive, updating it to 1. This means we can now form all consecutive values up to 1. Next, we process the second coin, which is 3. Here, we see that 3 is greater than max_consecutive plus 1, which is 2. This indicates a gap, meaning we cannot form all consecutive values beyond 1. As a result, we stop processing further and move to the final step. In the final step of the first example, we simply return max_consecutive plus 1, which is 1 plus 1, giving us the result of 2. This tells us that the maximum number of consecutive values we can form using the coins 1, 3, is 2. Moving to the second example, the input coins are 1, 1, 1, 4. After sorting, the coins remain 1, 1, 1, 4. We initialize max_consecutive to 0 again. Starting with the first coin, which is 1, we check if it is greater than max_consecutive plus 1. Since 1 is less than or equal to 1, we add this coin to max_consecutive, updating it to 1. This means we can now form all consecutive values up to 1. We now process the second coin, which is another 1. Again, we check if it is greater than max_consecutive plus 1. Since 1 is less than or equal to 2, we add this coin to max_consecutive, updating it to 2. This allows us to form all consecutive values up to 2. Next, we process the third coin, which is also 1. Once more, we find that 1 is less than or equal to max_consecutive plus 1, which is 3. Adding this coin to max_consecutive updates it to 3. At this point, we can form all consecutive values up to 3. The process continues as we move on to the next coin. The fourth coin in this example is 4. When we check if 4 is greater than max_consecutive plus 1, we find that 4 is less than or equal to 4, meaning it can be included to extend the range. Adding this coin updates max_consecutive to 7, allowing us to form all consecutive values up to 7. Finally, we return max_consecutive plus 1, which is 7 plus 1, resulting in an output of 8. This means the maximum number of consecutive values we can form using the coins 1, 1, 1, 4 is 8. Now, for the third example, the input coins are 1, 2, 5. After sorting, the coins remain 1, 2, 5. As usual, we initialize max_consecutive to 0. Starting with the first coin, which is 1, we check if it is greater than max_consecutive plus 1. Since 1 is less than or equal to 1, we add this coin to max_consecutive, updating it to 1. This means we can now form all consecutive values up to 1. Next, we process the second coin, which is 2. Checking if 2 is greater than max_consecutive plus 1, we find that 2 is less than or equal to 2, so we include it. Adding this coin updates max_consecutive to 3, allowing us to form all consecutive values up to 3. Finally, we process the third coin, which is 5. Here, we see that 5 is greater than max_consecutive plus 1, which is 4. This indicates a gap, meaning we cannot form all consecutive values beyond 3. At this point, we stop processing and return max_consecutive plus 1, which is 3 plus 1, giving us a result of 4. Therefore, the maximum number of consecutive values we can form using the coins 1, 2, 5 is 4. To analyze the time complexity of this solution, we start by examining its key components. First, the input list of coins is sorted in ascending order. Sorting an array of size n requires n asterisk log n time, which is a standard complexity for comparison-based sorting algorithms like timsort, used in Python. Next, the algorithm iterates through the sorted list of coins. In this iteration, we process each coin exactly once, performing constant time operations like comparisons and additions during each step. This contributes an additional n time. When we combine these two steps, the sorting process dominates, as n asterisk log n grows faster than n. Hence, the overall time complexity of the solution is n asterisk log n. Now, let's consider the space complexity. The primary factor here is the auxiliary space required by the sorting operation. Most comparison-based sorting algorithms, including timsort, use n extra space. Apart from this, the algorithm only uses a few additional variables, such as max_consecutive to track the current range and loop variables for iteration. These require constant space, or O1. Since the sorting step dominates the space usage, the total space complexity of the solution is n. Let's delve into the best, average, and worst-case scenarios for this algorithm. In the best case, if the coins are already sorted, the algorithm still needs to sort the array as part of its process, resulting in n asterisk log n time complexity. The subsequent iteration step remains n, so the overall complexity does not change. Similarly, in the average case, the algorithm consistently sorts the input and iterates through it, maintaining a time complexity of n asterisk log n. Even in the worst case, where the input coins are completely unsorted, the sorting step determines the overall complexity, which remains n asterisk log n. To put this into perspective, a brute force approach would involve generating all subsets of the coins array to calculate possible sums. This would take 2 to the power of n time and is impractical for larger inputs. The optimized approach presented here avoids this inefficiency by sorting the coins and iterating through them linearly, constructing the range of consecutive sums incrementally. This is why the current solution is far more efficient, with a time complexity of n asterisk log n. Finally, let's discuss why this algorithm is correct. The key lies in the greedy approach. Processing the coins in ascending order ensures that we always try to extend the range of consecutive sums in the most efficient way. At each step, we check whether the current coin can bridge the next gap in the range. If the coin's value is greater than max_consecutive plus 1, it means a gap exists, and the range cannot be extended any further. On the other hand, if the coin's value is within the allowable range, adding it to max_consecutive guarantees that all sums up to the new max_consecutive can be formed. This logic ensures that the algorithm is both correct and optimal. In summary, the final complexities of the algorithm are as follows. The time complexity is n asterisk log n, dominated by the sorting step, and the space complexity is n, determined by the auxiliary space required for sorting. When working on this problem, there are several common mistakes to watch out for. First, not sorting the array is a frequent error. Since the solution relies on processing coins in ascending order to build consecutive sums, skipping this step can lead to incorrect results. Sorting ensures that each coin is added in the correct sequence, which is crucial for maintaining the logic of the greedy approach. Another misconception is starting with the assumption that all coins must be used to form the maximum range of consecutive values. This isn't necessary. The goal is to form all values up to the maximum reachable range, not to use every coin. Overcomplicating the solution with backtracking is another trap. Although backtracking might seem like an option, it's computationally expensive and unnecessary since the greedy approach is both simpler and optimal. Additionally, it's important to test for edge cases, such as an empty array or an array with just one coin. For example, if the array is empty, the result should simply be 0. Lastly, a critical part of the solution is correctly updating the consecutive range as you add coins. If this step is overlooked, gaps in the sequence can occur, leading to an incorrect result. Paying close attention to these points can help you avoid common pitfalls and implement the solution effectively. Now, let's focus on insights that can help you during an interview. This problem is a classic example of a greedy algorithm. The key insight is that sorting the coins and then iteratively extending the reachable range guarantees that all values up to the current range are covered before moving forward. It's important to understand and clearly explain why this works. For instance, by processing coins in ascending order, each new coin adds to the smallest possible gap in the sequence, ensuring no values are skipped. Additionally, you should be ready to discuss the trade-offs of different approaches. For example, brute force methods, like generating all subsets of coins, are infeasible for large inputs because their exponential complexity becomes prohibitive. A better strategy is to focus on clarity. Walk through an example to show how the range expands step by step as each coin is processed. This demonstrates your understanding of the approach. Finally, don't forget to explicitly mention edge cases during the interview. This demonstrates thoroughness and shows the interviewer that you've thought carefully about all possible inputs, including edge scenarios like an empty array or very small datasets. This problem also shares similarities with other greedy algorithm problems, so understanding those can deepen your grasp of the underlying concepts. For example, LeetCode 406, queue reconstruction by height, involves sorting and processing elements in a specific order, much like this problem. LeetCode 135, Candy, is another greedy algorithm where the goal is to allocate resources while maintaining constraints. Similarly, LeetCode 376, Wiggle Subsequence, requires you to carefully handle elements to maximize sequence length. Lastly, LeetCode 322, Coin Change, focuses on forming specific values with coins, though it uses dynamic programming instead of a greedy approach. Speaking of alternative approaches, brute force methods, such as generating all subsets and computing their sums, are possible but computationally expensive due to their O(2 to the power of n) complexity. Dynamic programming is another option, where a table tracks all sums that can be formed. While feasible, this method has higher space complexity compared to the greedy approach. The optimal solution remains the greedy method, sorting the coins and iteratively updating the reachable range. With its O(n log n) time complexity for sorting and O(n) for the range calculation, it provides the most efficient balance of speed and simplicity. Great job! To wrap up, we reviewed how sorting and a greedy approach help solve problem number 1798 efficiently. We also discussed its complexity and key takeaways. Thanks for joining, and don't forget to like, share, and subscribe for more problem-solving insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!